Our goal now is to calculate the electronic structure of a graphene ribbon. So we again open Quantum Honeycomp, and in this menu where we have the different systems that we can calculate, we are going to choose the 1D systems ribbons. This window will open up, and in here you again can tune the parameters of your Hamiltonian as magnetic fields, Zeeman fields, and so on, sublattice imbalance. You also have this part where you can change the geometry of your system, so you can go from honeycomb to armature to even square lattice. And in this part here you have again the buttons to tune the electronic interactions in your system. So we are going to start with a honeycomb zigzag ribbon, and we are going to see how is the electronic structure. So first you have always to press this button here, ground state, and afterwards we press show band structure, and we will see the band structure of a zigzag ribbon, which is something like this. Well, most of you already know that these bands in here are states which are located on the edges, but we can also check this. So we only have to press this button here, and the local density of states will show up, as you see right now. So the ribbon, it's something like infinite in this direction, infinite in this direction, and this is your upper edge and this is your lower edge. And these big balls here represent your density of states. So what we can do now is we can add electronic interactions to this system and see how the system becomes metallic or insulating upon electronic interactions. So we turn on electronic interactions. We are going to make our ribbon a bit smaller so the calculations runs faster, and first we see how the electronic structure is without interactions. And now we will add interactions, and we will use a ferromagnetic initial guess. As you know, the Minfield-Haber interactions, which are the kind of calculations which are implemented here, require some initial guess for your solution. And in our case, we are going to try two guesses. First, the ferromagnetic one, and then the anti-ferromagnetic one. So we'll start with the ferromagnetic one. We turn on the interactions, we calculate the ground state, and we show the band structure of your system. And as we see here, we got a band splitting in comparison with the non-interacting case. You may wonder what is the spin flavor of these bands in here, and you can easily get that if you change the bands color option to off plane S. We calculate again the band structure, and what you see is that your bands that became splitted, they were actually spin splitted. So the occupied band is the blue one here, and the unoccupied band is the red one here. The next thing that we can try is to do again the Minfield-Haber calculation, but with an initial guess different. So we are going to try the anti-ferromagnetic guess. We calculate the ground state and we show the band structure of your system. And as you see, the bands right now, they look like a bit messy in terms of color. And the reason of this is because the ground state of this system now is anti-ferromagnetic between the edges, something that you can easily check if you press the show magnetism button. So this is going to take a while, and you may wonder what is the difference between the energy in here and in here. So in here we have a metallic state, and in here we have an insulating state. What it turns out is that the antiferromagnetic state is actually the one with less energy, and you can kind of understand that because this system here is metallic, this system here is insulating. Or you can also try to understand that in terms of the RKKY interaction between the different edges. So this is the magnetic structure of the antiferromagnetic state, and you see that most of the magnetic moment is located on the edge, whereas the bulk is almost completely non-magnetic. So this is the end of the second tutorial, and thank you very much.